Welcome to Section 2, Part 2 of the training course on demographic evaluation of age and sex data. Today, we're going to be covering the investigation into the age characteristics of the population. We'll be talking about how data on age are collected in censuses or surveys, how they're recorded in vital registration systems. And we'll be talking about the various investigations into the age characteristics of the population that might give us some insight into the overall quality of our age data. We'll be talking about age heaping, age omission, age exaggeration. We'll cover some measures of age heaping, as well as a brief description of what we term age ratios, all as various diagnostics of how one can interpret and evaluate the quality of one's age data. As I said in the previous video on this training course, the age and sex structure of a population gives the fundamental insight into the demographic characteristics of the population you're studying. In general, we would look at the age and sex structure together. That is, to look at the age structure of men and women separately. But here, for reasons of clarity, we'll be talking first about looking at the age structure, and then, in a subsequent video, look at the sex structure. The investigations into the age structure and the sex structure will provide clear indications of errors relating to heaping, omission, and age exaggeration. When we work with data on age, we have to ask ourselves the essential question: how were those data collected? There are two approaches to collecting data on age. The more preferable is to ask the respondent their date of birth. This is more exact and less prone to age heaping error because the age is derived then from the date of the survey or the date of the interview or the date of death in the vital registration system, differenced from their reported date of birth. However, to collect information on age from their date of birth, that requires that most of the population are date aware and are aware of their exact birth dates. There may still be errors in the data on age collected from dates of birth. For example, there may be a preference for round years of birth, that is, people rounding their year of birth to years of birth ending in a 0 or a 5. Likewise, there may be errors associated with particular events in a particular context where there was mass registration of the population. For example, in South Africa in 1994, a large proportion of the population was registered to vote in elections for the first time, and the population and the voters had to register their on the voters' roll with their date of birth. And that might have led to certain heapings of ages and dates of birth defined by the timing of their registration for those elections. Less preferable than asking respondents their date of birth is to ask respondents their age. This is usually less accurate as a result of either misunderstanding of the question, that the respondent might provide an answer of their age classified by their last birthday, their immediately upcoming birthday, or their nearest birthday. We'll tend to find that ages might be rounded to the nearest age ending in a 0 or a 5. And we might find that infants are reported as being age 1 and not age 0 in the population. So in general, it's always preferable, if your population is data aware, to collect information on age from the reported dates of birth, and then for the analyst to derive those ages directly themselves from those data. In general, in most populations, in most societies, when we refer to age as being age at the last birthday. So if I say that my age is 35, that means at my last birthday, I turned 35 years of age. In general, for most demographic analysis, we work with data grouped into quinquennial or 5-year age bands. The typical demographic bands which demographers and analysts use are those from age 0 to 4, 5 to 9, 10 to 14, etc. And we do this to avoid the problem of excessive noise in the data and to avoid the problem of heaping of ages, particularly on 0s and 5s. But it's always essential, before moving directly into the analysis of data by 5-year bands, to investigate the single year age data first, as you might get a much more refined understanding of the characteristics of the data that one is looking at. Before starting one's age investigations, you need to be alert to and understand how the data on age was collected or calculated. Was it asked from a direct question on age last birthday, or was it derived from a question asking people to report their dates of birth? In any survey or any inquiry, there will always be people whose ages are not reported, possibly because the respondent was unaware or it said they did not know how old a certain person was. And the question then is, what do we do with that information? Do we ignore it and report it in our tabulations as age unknown? You might want to distribute those unreported ages across the population in proportion to the population with known ages. But in that case, you'd have to be fairly certain that the population with unknown ages are essentially similar to the population with known ages by all major characteristics. Or thirdly, we could distribute those unreported ages by other characteristics. For example, we could make an inference about age depending on the woman's reported number of children or her level of education. A further consideration before one starts one's age investigations is what to do about the open-ended age groups. For example, the grouping of all people aged 85 and older. We want the elements in that open-ended age group to be large enough for robust analysis, but not so large that you lose valuable information. There's no explicit guidance on the choice of starting point for those open-ended age groups, and so perhaps the best advice is to use what has been used before or what is being used by other entities who work with the same data, so the National Statistical Office or the agency responsible for the civil registration and vital statistics data. With historical data, you need to be particularly alert to the possible use of error codes that may be mistaken for age. In many old censuses from the 1960s and 1970s, age was only recorded as a 2-digit variable. And in those censuses and in those surveys and in those inquiries, a response of missing or not reported might have been given an error code, say, of 98. And that might then result in those error codes being mistaken for age in your analysis. With the use now of more modern censuses and survey instruments, those error codes tend to be 3-digit error codes. For example, 998 might be the error code for missing, and that would then not arise in your data and not lead to a potential mistaken of that error code for the age, because no human being reaches the age of 998 years. When performing age investigations, I want to offer 2 perhaps controversial pieces of advice. The first is, don't draw population pyramids for data evaluation. Population pyramids are very useful for public communication of results, but are exceedingly time-consuming to produce in Excel. And there are faster and better ways of getting useful information without having to spend a whole lot of time trying to produce a population pyramid using Excel. Similarly, there are many different indices of age structure or heaping in the data. For example, the Whipple's index or the Myers index, but those are really of rather limited value. And again, one can gain as much information from visual assessment of the data as one can do from the calculation and derivation of an index of age structure, such as Whipple's or Myers. However, in this training video, we'll cover them here for completeness, but the recommendation is that they are not used for data evaluation. In an age investigation, the essential first step is to plot the numbers enumerated at each age and by sex. First, we do it by individual years of age, and only then, having done that exercise, we will proceed to looking at the same data grouped in conventional 5-year age groups. I just note here briefly that there's a very useful formula which you can use in Excel if you don't have the data grouped into 5-year age groups. And the formula is given over here, where the age group is given by 5 times the integer portion of the reported age divided by 5. If you think about this, someone who says, or a part of a tabulation of people aged 13, 13 divided by 5 is 2.6. The integer portion of that is 2. 2 times 5 is 10. And so someone in age 13 would be in age group 10, or the 10 to 14 age group. Someone aged 15, 15 divided by 5 is 3. The integer portion of that is 3. 3 times 5 is 15. So someone aged 15 would be in the age group 15, which would be used to denote the 15 to 19 age group. We can then use the Excel SUMIF function of these age groups to produce a tabulation by 5-year age groups. And I'll be demonstrating that in the spreadsheet which accompanies this particular training video. When we look at age data, what we expect to be able to look for, or expect to see in the data, are indications of age heaping, age omission, and age exaggeration. Along the way, we'll also gain clues or pointers to other demographic factors, recent fertility trends, the age pattern of mortality, and in many situations, the extent of migration into or out of that population. In general, as noted already, age heaping tends to be on ages ending in a 0 or a 5. However, if age is derived from the year of birth, there may be heaping on ages corresponding to a year of birth ending in a 0 or 5, with the respondent choosing and electing to round up or down their year of birth to the nearest year ending in a 0 or 5. Depending on when your census or survey is conducted, the calendar year in which that is conducted, that might result in heaping in other ages associated with the year of birth ending in 0 or 5 relative to the year in which your survey or census was conducted. And as noted already, there may also be age heaping associated with more complex patterns of heaping, for example, that with the South African voter registration in 1994. Omission of the population can manifest itself and can be identified by looking at the age data. This tends to manifest in most developing countries, particularly at the youngest ages, ages 0, 1, and possibly ages 2 and 3 as well. There's a real risk that omissions of the very young ages in the population might create a misleading impression of recent fertility patterns. Omission of infants would imply that fertility had been lower in the year or so before the census survey than it actually was. And so before leaping to a conclusion about the fertility patterns, you need to ask yourself whether that might have been created by the omission of young people. Sex-specific omissions may also occur in some societies where women are differentially underenumerated. But there are also other possible explanations for sex-specific differentials in your age structure of the population. Crucially, these might be migration, which we'll see very clear instances of in the examples coming up. It might be related to war, famine, and in some parts of the developing world, diseases such as HIV that typically affect different age groups for different sexes differentially. Finally, when we talk about age exaggeration, this tends to manifest itself at the very oldest ages, particularly in societies where age is highly venerated or respected. And age exaggeration will result in there being apparently many, many more very old people than could plausibly be in that population with one's knowledge of patterns of mortality and the age structure of the population. Before moving on to the graphical analysis of age data, there are several questions which we need to routinely ask ourselves in conducting a graphical analysis. The first thing is to ask ourselves, what are we looking at? What does the plot show? What are the axes horizontally and vertically? Are the vertical axes presented as numbers or proportions, for example? We need to ask ourselves, what is actually being plotted on those in that graph? And we have to ask, does the plot show what you think it does? We have a prior understanding of what a typical age-sex structure of the population looks like, and we'd want to know that that plot is showing us what we think it does, or it might be an indication that the data have not been extracted correctly. We'd ask ourselves, what features do we see in our data? What are the characteristics of what we have? Do we see evidence of omissions or age heaping, for example? We might be able to say, we think we can see a demonstration of the effects of migration in our age-sex structure of our population. And then we have to ask ourselves, how might we explain what we see when we look at those features of the data and those characteristics? And then finally, we'd ask ourselves, how do we go about testing those explanations? And with what data might we want to test whether our suppositions and our hypotheses are correct? So in the next few slides, I'm going to go through some age-sex plots of 3 different countries' populations drawn from their censuses in the last 20 years. The first example is that of Nepal in their 2001 census. And this is a plot where the x-axis going along horizontally here at the bottom is age measured in single years of age, and going up vertically here is a count of the population by age of the population of Nepal in 2001. The red line in this plot is the female population, while the blue line is the male population. What we can see in this data is some very typical characteristics of a population. We can see that there are far fewer people at younger ages than there are at older ages. That would be typical of a young, relatively young population with historically high levels of fertility and probably quite high levels of mortality. We can also see, and it's particularly evident from ages 30 onwards, this heaping at very round digits. That's age 35, 30, 35, 40, 45, 50, etc. And we can see how the numbers of the population, say at age 35, are almost 3 times higher than the population aged, say, 36 or 37 in the population. So we can see that there's extreme age heaping in these data. If we look here on the extreme left-hand side, there seems to be a relatively small number of children aged 0 and 1 and 2 in this population. Now, this could potentially be an indication that there's been a sudden and very rapid decline in fertility in Nepal. But bearing in mind what I said earlier, the more likely prior explanation is that there's been differential omission of very young children in the census, and that would be something which is worth looking at. In general, when we look at the population by single years of age, the numbers of males and females are broadly consistent with each other, although we can see here, for example, of men in their 20s and 30s, a relative shortage of men and a relative surfeit of women at other ages. These are all things which might need to be subjected to further investigation. If we take these same data and plot them in 5-year age bands, what we have now is still the population of Nepal as revealed by the 2001 census, but now along the x-axis here horizontally, we have the population grouped into 5-year age groups, 0 to 4, 5 to 9, with an open interval age 95 and older. Going up the y-axis, we have the count of the population in Nepal as revealed by the 2001 census, and again the red line represents women and the blue line represents males. Again, what we can see here is we can see this very evident relatively small number of the population aged 0 and 4 relative to the population aged 5 to 9. When we looked at it by single years of age, that was being largely driven by the population's ages 0, 1, and 2. And so this really does start to lead us to believe that that apparent decrease in the population aged 0 to 4 in Nepal in 2001 is more likely to be as a result of underenumeration of very young children. From ages 15 through to about age 35, there's a clear deficit of males relative to females, which did not exist up until age 15. The most likely explanation for this is likely to be that of labor migration of young adult males moving to other countries, neighboring countries, for labor and for employment purposes. But that is something which we'd have to find other evidence for: sociological, economic, other data sets, some understanding of the population of Nepal and its socioeconomic dynamics and patterns, to say whether that might be the most likely explanation for this apparent deficit of males relative to females in those young adult ages. There's a curiosity here at the, around about age 55, where there would appear to be a relative surfeit of males relative to females in that population. But overall, when we can look at this plot by 5 years of age, we can see how the noise is reduced relative to the plot by single years of age. And we can see how that this effectively here would represent a population pyramid rotated on its side. You can imagine the typical population pyramid has age going up and the quantities going along the x-axis. And so this is a population pyramid effectively rotated through 90 degrees and with both series plotted against each other. What we can see here is the very small numbers of the population at extreme old ages, much larger population at young ages. And so we can make those same inferences about the overall characteristics of the population of Nepal as we could have got from drawing a population pyramid without actually having to draw one. The second example I want to use is that of Bahrain, as revealed by the 2010 census. Here, along the x-axis, again, is the population in by single years of age. You can see there's this small little deviations by single years of age, and going up the y-axis is the count of the population at each of those single years of age. Again, we can see that there are relatively few people over the age of 60, and there's an open age interval at age 85, which is quite a lot larger than the population at either age 80, 81, 82, 83, 84. And that is a consequence of aggregating all that data together from age 85 and older. At the other extreme, there's a relative deficit relative to those age 1, 2, 3, 4, and 5 of those aged 0. And again, that would most likely be explained by an underenumeration of children aged 0 in the census, rather than some sudden catastrophic decline in fertility in this population over the immediate year preceding the 2010 census. But what really stands out in this plot by single years of age is this plot of the male population by single years of age, where the numbers of males and females are broadly equivalent to each other till about age 18. And then the population of males increases dramatically, reaching a maximum around about age 30, and then falls off very rapidly until, again, roughly equals numbers of males and females by age 65. And the most plausible explanation for this is differential male labor-related migration into Bahrain around the time of the 2010 census, and that the pattern of labor migration might have persisted for some time before that. There's an indication of a lesser, but nonetheless meaningful pattern of female in migration to Bahrain. You can see the sudden increase of the female population between ages 20 and 30, which then gradually reduces again to about age 65, where the number of males and females is again roughly equivalent. And again, that is likely to be an indication of lesser female migration to Bahrain, possibly for domestic service, but far lower levels of migration than the population of males. Looking at the same data by 5-year age groups, we can see here that the relative deficit at age 0 is not readily apparent in the comparison of the data for those aged 0 to 4 relative to those aged 5 to 9. And we can see that the impact of the male labor migration into Bahrain amongst the young adult ages, and a much less the effect for women. But the data are far smoother when one looks at about 5 years of age, and again describes a relatively young population. And when we look at the data by single years of age over here, there are no real strong indications of heaping. There's a little bit going on here that would appear to be age 72, 77, and 82. And we'll look at that just now when we look at the underlying data. But clearly, there's far less age heaping in this population than there was in the case of the Nepalese data. The third example I want to use is that of South Africa as revealed by its 2011 census. Again, along the x-axis horizontally here, we have the population by single years of age. You can see the variation by individual years, and we have a count of the population by age and by sex as revealed by that census. Like the Bahraini data, there's limited indication of a very obvious omission of children under the age of 1 or 2 in the census, but there is a very curious pattern of the population after age about 5 through to about age 20, where the population falls and then rises. And one of the questions one would have to ask oneself is this a consequence of differential omission of young adults in the South African census of 2011? Or was there a very curious pattern of fertility decline and then fertility increase over the tail end of the 20th century and the beginning of the 21st century? And that would be something which would need to be evaluated and investigated in much greater detail. At the extreme ages, we can see that there are many more women than there are men. And there's some indication, again, of heaping at certain ages, at 71 and 81 in these data, for example. But again, nowhere near the extreme version of heaping as we saw in the Nepalese data. We can see that there are far more women after about age 40 in this population than there are men. Now, this might be explained possibly by labor migration, but that is unlikely in the South African context, and with knowledge of the South African context, that we would not expect large quantities of males moving out of South Africa for economic reasons. More likely, what this is a manifestation of is of the much higher level of mortality amongst South African men relative to South African women. We know that in South Africa, unnatural deaths, such as homicides, murders, etc., are much greater amongst men than amongst women, and we have one of the highest burdens of unnatural disease in the world. And so this relative deficit of males in our population aged 40 is likely to be driven by that. When we look at the data by 5 years, in 5-year age groups, so along the x-axis here, we have the age groups 0 to 4, 5 to 9 with an open interval of 100 plus, and the counts of the population by age and by sex. And we can again see that relative deficit of the population from ages 5 to about age 20. And we again have to ask ourselves whether this is a real phenomenon, demographic phenomenon in the country, or whether it is a result of differential omission of young adults. The effect of the much higher male mortality in South Africa is again evident here by the relative shortfall of males in the population relative to females. And that is something which we can explain by appealing to our prior knowledge about the nature of burden of disease and mortality rates in the country. What I want to quickly go through now then is to show you how one derives these plots using Excel. So I'm going to pull up onto my screen now, and it should be visible to you, the spreadsheet which I have used to produce those plots. And this spreadsheet is available to you on the training workshop file download site. What we have here is for the three countries, Bahrain in 2010, Nepal in 2001, and South Africa in 2011, was an extract from the UN Stats Division on the population by single years of age, 0, 1, 2, 3, 4, 5. And in each case, going to, in Bahrain's case, an open interval of age 85 plus. That's how the data were provided to us. In the case of Nepal, it was from those aged 98 and older, and for South Africa, it was aged 100 and older. And what we can see here in the second column in each case here is the age group, which is then derived from those single years of age. If you look at this formula over here, for example, for 4-year-olds, that says that the group associated with age 4 is 5 times the integer portion of 4, cell A7, divided by 5. 4 divided by 5 is 0.8, so the integer portion is 0. Multiplied by 5 would still be 0. And you can see then how the 0 to 4s are all put in age group 0. The 5 to 9s are put into age group 5 to the 5 age group. And we just need to manually modify the open-ended age group to say that all people age 85 plus would be in the 85 age group. Of the age groups from the single years of age to derive directly a tabulation of the population of Bahrain in 5-year age groups. And here we use the Excel SUMIF function to derive these numbers. So, for example, the female population of Bahrain, as revealed by the 2010 census, who are aged 0 to 4, which by our coding of the age group was age group 0, is derived using the Excel SUMIF function. And this has the following arguments. It says SUMIF, and so add up all cases if, and the range here is B3 to B88. So if all those age groups, SUMIF all of those age groups, if those age groups are equal to cell S3, which is age group 0. So, and we'll then add up the contents of cell C3 to C88, which is the population of females by single years of age. So what this is doing is saying, add up all the numbers in this column, cell C3 to C88, if the age group is equal to 0, and the age group is defined in that column. And in the next row down, that will be then saying, add up the same values, C3 to C88, the population of females by single years of age, if your age group, column B, is equal now to 5. And that will allow us to then directly derive the populations by 5-year age groups. And that can be a very useful trick if you do not have the data by 5-year age groups provided to you. Moving on, I want to talk briefly about the summary measures of age heaping, which I referred to at the beginning of this video. And here we talk about Whipple's index and Myers index. Whipple's index provides a summary measure of age heaping on ages ending in 0 and 5. The method assumes, unrealistically, that the population within any 5-year age group, 5 to 9, 10 to 14, 15 to 19, is rectangular. In other words, that there are equal numbers at each age in the same age group. Typically, we calculate Whipple's index only for ages 23 up to 62 to avoid common problems at the youngest and oldest ages. We want to avoid the problem of the effect of mortality at oldest ages, which will clearly violate the assumption of rectangularity, which underpins the method. And we want to avoid the effect of omission and heaping at younger ages in our data. To calculate Whipple's index, we calculate it using the formula. Whipple's index is the sum of the populations at exact age 25, 30, 35, 40, up to age 60, divided by the sum of all people aged from 23, 24, 25 to 61 to 62, and dividing that by 5, because we are going to be working in 5-year age groups. And we're going to multiply that number by 100. The value of Whipple's index will typically take values in the range of somewhere around about 100 up to 500, 500 being the absolute maximum value. If it takes on the value of 100 in that age range from 23 to 62, that would mean that your data are in effect rectangular. There is no heaping on age data on 0s or 5. If your Whipple's index came out at a value of 500, it would mean that your data were completely heaped on ages 0 and 5. And if it comes out to be slightly less than 100, that would apply an aversion to ages 0 and 5. So people are actually unheaping their ages on 0 and 5, but they might be heaping it according to some other measure, for example, year of birth. When we derive our value of Whipple's index, a value of less than 105 is often taken to mean that the data are highly accurate. Between 105 and 110 would be regarded as fairly accurate data. Between 110 and 125 as approximate data. Between 125 and 175 would be rough data, and a value of greater than 175 would be classified as very rough data. I will demonstrate how this is calculated just now using the spreadsheet and the data we have. The alternative is Myers's blended index, which is an alternative approach which tries to avoid the problems associated with Whipple's index. Myers's index produces an index of preference for each terminal digit, so any age ending in 0 or 1 or 2 or 7 or 8 or 9, indicating from 10% of the proportion of the total population reporting ages with that given terminal digit. The theoretical range of Myers's blended index ranges from 0, saying there's no preference for any given digit, to 90, complete preference for a single terminal digit. And again, we implement this in the spreadsheet, which is accompanying this session. When we calculate these measures from our data, what we find is that the measures really do not reveal a whole lot more than we had already seen in the data. If we look at the calculation of Whipple's index for Bahrain, it says that Whipple's index is about 100. In other words, the data are highly accurate. There's no evidence of age heaping, which is what we saw in that plot. The data for Nepal, however, has a Whipple's index of over 200, which would be classified as very rough. And we saw that in our population age sex plot of the data. And likewise for South Africa, in fact, the Whipple's index for South Africa comes out to be less than 100, implying the population has no distinct preference. In fact, an aversion to reporting ages ending in 0 or 5. Likewise, Myers index, which runs from 0 to 90, we see in Bahrain and South Africa values very close to 0, indicating that there's no real heaping of the data by any terminal digit. And in Nepal, we see a relatively high index, 18, which again is indicative of fairly extreme age heaping. And so the point being here that the calculation of Whipple's index or Myers's index adds very limited information to what we could have got from our plot. And it's for this reason that we don't recommend the derivation of these indices as part of your routine data evaluations. I just want to demonstrate for you, though, how these data, how the estimates are derived from the data. And so what we have here for Bahrain, Nepal, and South Africa, these are the total populations derived from sorry, at each age from the data extracted from the UN Stats Division. And in order to calculate Whipple's index for Bahrain over here, we can see it's given by 100 times the cells at age 25, 30, 35, all the way up to 60, divided by the sum at all individual ages from ages 23 to 62. And so we can calculate Whipple's index directly from those population age structures by single years of age. The calculation of Myers's index is much more complicated. What we do is we work with ages ending in a 0, so 10, 20, 30, 40, 50, 60, 70, 80, up to a maximum of age 80 in these data. And we add up the number of people who report an age ending in a 0 from age 10 plus A would be the age to 10. This would be the population with ages ending in a 1, 11, 21, up to age 81, etc. And we do the same thing then for the population reporting a terminal digit ending age for the next age groups after that. So this would be the sum of ages ending in 0 at 20, 30, 40, 50, 60, 70, and 80. The derivation of Myers' blended index is covered in this panel over here, where it derives what Myers terms a blended population, which is a measure of this population, a weighted total of this population from the two different groups of people, either from age 10 or from age 20, weighting those two quantities differentially. And they derive a blended population, the distribution of that blended population, and therefore a measure the deviation of that population from 10%. Because if ages were distributed equally over each ages, then each age would end in ending in a 0, 1, 2 should account for 10% of the population. But as you can see, the derivation of this index is not only fairly complicated, but doesn't really tell us anything more than what we would have got from our age plot. And it's for that reason that we don't recommend the derivation of Whipple's or Myers' index. Finally, in this session, I want to cover briefly the idea of an age ratio. In the absence of sharp changes in fertility or mortality, and without significant levels of migration or other distorting factors, the enumerated size of a particular cohort should be approximately equal to the average size of the cohort just before and just afterwards. In other words, that the age ratio for a particular cohort of people in a particular age group to the average of the count for the age cohorts either side of them should be approximately equal to 1. Or if you multiply by a constant of 100 to a value of 100. Significant departures from that expected value of 1 would indicate the presence of census or survey error in the census enumeration or of other factors. We would calculate that age ratio based on the description I've just given as the number of people in the age group X to X plus N divided by the number of people in the age group immediately before that, the age group X minus 5 up to X minus 5 plus N, and the population X plus 5 to X plus 5 plus N. And that would give us the age ratio between ages X and X plus N. We include that factor of 2 because there are 2 elements in the denominator, and we want the 2 to more or less average out. But bear in mind that a wrongly low value in the numerator here would mean that that value would be too low relative to the values you're dividing it by either side. And so that age ratio would be too low. But when you calculate it for the next age group, if that value N and X was too low, well, then when you calculate for the next age group, that value will appear in the denominator, which means you'll be dividing by a value which is too low, which will inflate the value of that age ratio. And so errors in the data will tend to come through as a kind of sawtooth in your plot of the age ratios. And we can see this in the plot for the 3 data sources which we used originally for this exercise of Bahrain in blue, Nepal shown here in red, and South Africa shown in green on this slide. And what we're showing here are those derived age ratios by 5-year age groups and the value of those age ratios going up the y-axis. I've just marked with an asterisk over here that in the case of Bahrain, that age ratio for age 85 to 89 is the start of the age interval there. For Nepal, 95 to 99 was the start of the open age interval there. And for South Africa, the age interval starts at 100. When we look at these data, we can see that in all 3 countries, from about age 35 through to about age 55, those age ratios are indeed very close to 1. The data for South Africa are fairly close to 1 at all ages up to 65, and then start developing what I've described as a characteristic sawtooth kind of pattern, which is indicative of age errors in your data or age heaping of the data or other factors perturbing your data. And so we can see, for example, in the Bahraini data that those age ratios rise quite high to almost a level of 1.2, because in that age group of the 25 to 29s, there's such extreme in-migration into that population relative to the population age 20 to 24 or 30 to 34 that the age ratio gets distorted. And so one can use these age ratios as a further indication as to possible clues and hints in the errors in the data. We can see here, for example, for Nepal, amongst the 5 to 9-year-olds, so that age ratio for Nepal 5 to 9-year-olds would be the population aged 5 to 9 multiplied by 2, divided by the population aged 0 to 4 and 10 to 14. But we knew from the age plot, the population 0 to 4 in Nepal was relatively low, and that has caused that value to be inflated at that point. And so we can use age ratios as a further mechanism to gain some further insight into the quality of our age and sex data. We've come to the end of section 2 of part 2 of this training course. A reminder that if you have any questions or queries on this material, please email me, thomas.moultrie@un.org, and copy it to the UNESCAP CRVS team, unescapcrvs@un.org, and I'll do my best to answer questions, either by return of email or in the first plenary session, which we'll be joining each other for in approximately 10 days' time. Thank you very much, and thank you.